Have you ever looked at a solar panel and wondered, how in the world do they make that? It seems like magic, doesn't it? A flat, dark rectangle silently turning sunlight into electricity. Well, it's not magic, it's science. It's a fascinating process that starts with beach sand and becomes a high-tech device that can power your home. It's an amazing journey, full of heat, precision, and very cool engineering. Believe it or not, our story starts at the beach, or more accurately, in a quartz sand quarry. The main ingredient for most solar panels on Earth is silicon, the second most abundant element in Earth's crust, but it's not found pure, it's locked with oxygen as silicon dioxide, or silica. First, we separate silicon from oxygen, a high-energy foundational step. Silica and carbon go into a giant electric arc furnace at around 2,000 degrees size, over 3,600 degree dive. Carbon grabs oxygen from silica, leaving molten silicon. About 99% pure, metallurgical grade. For solar, we need far purer. Using the Siemens process, silicon reacts with hydrogen chloride to form trichlorosilane. It's distilled, like refining alcohol, to remove impurities. Iron, aluminum, boron. Then the ultra-pure gas is decomposed over heated silicon rods, slowly depositing ultra-pure polysilicon. After hundreds of hours, we get large, metallic-looking rods, our true starting blocks. Polysilicon is melted in a quartz crucible. For monocrystalline silicon, a seed crystal templates atom alignment as it's slowly pulled. The result is a single crystal ingot, think giant gray cylinder, with perfect order for easy electron flow. Polycrystalline cools in square molds, faster and cheaper, but with grain boundaries that impede electrons. Either way, we're ready to slice these crystals into ultra-thin wafers. Round ingots are squared for better packing, then mounted on diamond-coated wire saws. The moving wire slices hundreds of wafers at once, each about 160–180 micrometers, thinner than a human hair. Silicon dust is collected and recycled to make new ingots. Fresh-cut wafers have saw marks and damage. They're cleaned and polished into smooth, mirror-like wafers ready for cell processing. A perfect wafer alone can't generate electricity. We add tiny amounts of elements, doping, to create two layers inside the same wafer. Boron creates P-type silicon with positively charged holes. Phosphorus diffused into the surface creates an N-type layer rich in free electrons. Where they meet, a P-N junction forms a built-in electric field. A tiny, one-way street for electrons. Sunlight photons knock electrons loose, creating electron-hole pairs. The field pushes electrons to the N side and holes to the P side, creating voltage like a battery. Connect a wire, and electrons flow through a circuit to do work. That flow is electric current. To boost efficiency, we add an anti-reflective silicon nitride coating via PECVD to trap more light. Metallization prints thin silver fingers and bus bars on the front and aluminum on the back, then firing bonds the contacts. Our wafer is now officially a solar cell. Every cell is flash-tested and sorted by efficiency, mixing grades bottleneck strings like a kinked hose, thin copper ribbons soldered to bus bars, linking cells in series so voltages add up. Stringing is highly automated for reliable joints. Bad connections waste power as heat. Residential modules are typically 60 cells. Larger formats often use 72. Robotic pick-and-place positions delicate strings onto a strong, highly transparent tempered glass front. A transparent EVA sheet cushions and adheres when melted. A second EVA layer goes on top, sealing cells from both sides. A multi-layer backsheet adds moisture protection and electrical insulation for decades. We now have a sandwich of materials. Glass, EVA, cells, EVA, backsheet, aligned and ready for lamination. Precision alignment locks geometry before sealing. The laminator evacuates air, then heats and presses. Think high-tech panini press. At 150 degrees Celsius, 300 degrees Celsius, EVA melts and bonds glass, cells and backsheet into one weatherproof unit. An extruded aluminum frame adds rigidity, strong, lightweight, corrosion-resistant, sealed with silicone. A waterproof junction box connects internal ribbons to external leads and houses bypass diodes. If a section is shaded by a leaf or bird dropping, bypass diodes route current around it, protecting performance. Before shipping, each panel faces a final flash test under standard conditions. Sensors confirm Pmax, voltage, and current. A 400-watt panel must hit its spec. Modules are sorted so installers receive tightly matched pallets. EL imaging reveals hidden micro cracks and defects. Like ensadumartemuanin, omwaxkurin, ukexenwarenda, or berbarkalmai, berbatsabroy, were Jordan sir. Berbanan Monen Senburn Senso. Sample modules endure thermal cycles, 85° 85% RH damp heat, and heavy snow wind loads to certify durability. Only after passing this gauntlet is a design certified for sale and long-term warranties. These tests give confidence that panels on your roof are built to last for 25 to 30 years. From humble sand to high-tech modules, extreme heat, incredible purity, precise engineering, rigorous testing. This journey is part of our global transition to a sustainable energy future. Each panel is a small but powerful engine for change, silently doing its job day after day. They're forged in fire, sliced by diamond-dusted wires, and assembled with robotic precision. From factory to rooftop, every step is a link in a chain, only as strong as its weakest link. Obsessive quality control at every stage keeps weak links out, so the next time you see those dark rectangles, you'll know the complex story they hold. Science is cool, isn't it?